So in this example, we're going to look at a discharging RC circuit. So I give you a circuit as I show you in the diagram. It consists of a capacitor and a resistor. The capacitor has some initial charge, Q initial. It is connected to the resistor and current is allowed to flow at time t is equal to 0 seconds. And I ask, calculate the charge on the capacitor as a function of time for this discharging RC circuit. So, like in the charging RC circuit case, we can solve this problem using Kirchhoff's loop rule. So, first I'm going to start in the bottom left-hand corner of my circuit and I'm going to draw a path clockwise around my circuit. So, plus Q over C, that's the voltage across the capacitor, minus IR, that's the voltage across my resistor, is equal to 0. Now, plus Q over C is just Q over C, but I note that the current in the circuit is actually the negative of the charge on the capacitor. This is because charge is flowing off the capacitor, so negative dq dt is equal to I. And so when I divide through by R, I can simplify this down to Q over RC plus dq dt equals 0. And now let's just do a little bit of basic calculus. So I can rearrange my equation. dq over q is equal to minus dt over rc. I can integrate. I get natural log of q is equal to minus t over rc plus a, where a is just some constant. I tried not to use c for the constant just so we would keep the capacitance and the constant separate. So a is my constant. I can take the exponent of each side, so I get q is equal to e to the minus t over rc plus a. Well, we know if some exponent has a sum, we can split that up into e to the minus t over rc times e to the a. And I can take that e to the a and just redefine it as a new constant. So I'm going to redefine that as the new constant a. And so now we need to solve for constant a, and we can do that by plugging in our initial condition. So at time t is equal to 0, the charge on the capacitor is equal to Q initial. And so Q initial is equal to A. Plugging that back in, I get Q of t is equal to Q initial e to the minus t over RC. And just to show you what that looks like, I've plotted the charge as a function of time on the capacitor for various time constants. You can see when the time constant is very small, tau equals 1, the capacitor discharges quickly, and as it gets bigger and bigger, it takes longer and longer for the capacitor to discharge. So a few final thoughts. First, we solve a simple differential equation to get the solution for a discharging RC circuit. And I ask you, what would happen if I reverse the polarity of the capacitor? In other words, what would happen if I turn the capacitor around in the circuit?